Hey guys, welcome back. So we're going to go over the parts of energy that involve derivatives and integrals. So on your guys' equation sheet, work isn't equal to F dot R. It's equal to the integral of F dot dr. And so we're going to take the integral of what our forces are to find out what our work is. So I have work in the x direction, and I'm going to have work in the y direction. In the x direction, our function is going to be 3x squared, and it's going to go from 2 to 3. And in the y direction, I have 4 dy, and this is going to go from 3 to 0. So this is going to give me x cubed, which is going to give me 27 minus 8 joules, or 19 joules. This is going to give me 4y, which is going to give me 0 minus 12 joules, which gives me positive 7 joules. It would be an increase in kinetic energy because positive work increases energy, negative work decreases energy. And here is the explanation. The force on a particle is directed along an x-axis and given by F equals F0, x over x naught minus 1. Find the work done by the force moving the particle from x equals 0 to x equals 2x naught by plotting fx and measuring the work from the graph and integrating. So if we plotted it, we could take the area under the curve, which is essentially what an integral is. So my work is going to be the integral of x dx. I'm going to take this integral from 0 to 2x0. And so this is going to be f0 x over x0 minus 1 dx. So I can take the F naught from inside of there. All right, so this term would be x squared over 2x naught minus x. And so we plug in 2x naught. I would have 4x naught squared over 2x naught minus 2x naught would be my first term. My second term is just going to be 0. So I could cancel out an x naught. I could cancel out 2. And I have 2x naught minus 2x naught. So I end up with 0 joules of work. Instantaneous power is going to be how our work changes with respect to time. So we can take the derivative of the work function with respect to time. Power is also going to be a scalar, just like work is, and it has a unit of watts. We also know that power is equal to our force times our velocity. And so we can rewrite this as power is the dot product if we have an average force dot our velocity. And again, anytime you have a dot product between two vectors, you end up with a scale. Figure 714 shows a constant forces F1 and F2 acting on a box as the box slides rightward across a frictionless floor. Force F1 is horizontal with a magnitude of 2n. Force 2 is angled upward by 60 degrees to the floor and has a magnitude of 4n. The speed v of the box at a certain instant is 3 meters per second. What is the power due to each of these? Each force acting on the box at that instant? What is the net power? Is the net power changing at that instant? Okay, so I know that F1 is 2 newtons. I would say that's negative 2 newtons. And I know that F2 is 4 newtons, but only the horizontal component of it is contributing. So the net force is, I want to make sure that my calculator is in degrees, and it is going to be 4 cosine of 60 minus 2 gives us 0. So those forces are perfectly balanced out. R1, F1, is going to be negative 2 newtons times 3 meters per second, which would be negative 6 watts. P2 is going to be the 4 cosine 60, which is 2, positive 2 newtons times 3 meters per second, which is positive 6 watts. So our net would be the sum of the two, which was the 0. It wouldn't be changing because the net force is 0 in that direction, so the velocity is not changing. All right, so we know that this work is going to be equal to f of s dx integral from one end to the other. We can also figure this out by the area. A big part of this is they have you guys analyze potential energy curves. They don't show up on the other AP test. So I'm going to try to introduce these to you and try to make sense of them. So if you wanted to lift a bowling ball, and I did this for you guys, as the ball moves up, it's an increase in potential energy because the work is positive. The work is in the same direction as the displacement. The work done by gravity would be the opposite because the force of gravity is down and the displacement is up. So our work applied is equal to mgh. And we're going to assume that we're going to lift it up at a constant speed. So I could say that the work that was applied is equal to the change in potential energy. And these are positive because they're in the same direction. And they're also positive because it's an increase in energy. All right, so if we know that the force applied and mg are equal because there's no acceleration, it's F net equals 0, then the work done by gravity is going to be negative because my displacement is up and gravity is down. And that tells me that I have negative work when they're in opposite directions. So we could say that the work done by gravity is minus mgh or minus pe or minus u. All right, so looking at this another way, if I let go of the ball, the gravity is going to do positive work on the ball because now the displacement and the force are both going to be down. And the potential energy is going to decrease. So the positive work is going to be equal to the negative of the change in kinetic energy. So the field is always going to work to try to reduce the potential energy. So it's always trying to get it to be less and less and less and less. So now that we know that work is equal to our integral of f of x dx, which is also equal to our area, and we know that the work of the field is equal to the negative of the potential energy, then it would come to mean that our change in potential energy is going to be the negative of the work integral. So if the force is causing an increase in the potential energy, then our W and our U are positive. If the force is causing a decrease in the potential energy, then our change in potential energy will be negative. So our potential energy is the negative antiderivative of force, which is another word for integral, with respect to displacement. Then we can find the force by doing it the other way. So f of x is going to be equal to the derivative of the potential energy function with respect to x negative, or negative of the slope. So remember, the integrals are just areas, our derivatives are just slopes, or how that function is changing at the given time. So the area of a force position graph gives the work done by the force. The opposite of the area gives us the change in potential energy. And then the opposite of the slope of the potential energy versus position graph gives us the force acting on that particle. So f of x is going to be equal to negative du dx. All right, so we have potential energy curves, and they're going to show us how the potential energy is going to change. There are three. There are ones that are stable equilibrium, there are ones that are unstable equilibrium, and there are ones that are neutral equilibrium. What is equilibrium? Equilibrium is the same thing that it was in forces before. It's going to be when our net force is 0. So when our net force is 0 and our acceleration is 0. So what does that mean for us? The points of equilibrium are going to be where our graph has a slope of 0. So where is our graph going to have a slope of 0? We know that this happens at points like that. So this would be our equilibrium points. All right, so where here is my equilibrium point. My equilibrium point is here, and this is going to be a stable equilibrium. So there's a certain total amount of energy in the system that goes back and forth. And when the skater is all the way at the bottom, there is no net force on it. That's going to be our equilibrium. So when we have a stable equilibrium, that's going to be when a small displacement results in a restoring force that accelerates the particle back to the origin, its equilibrium position. So if you thought about, we push the skater this way, the force would be the negative of the slope. This slope would be negative, so a negative of a negative is a positive, and the force is positive, pushing it back. And it would put her towards the equilibrium point. When a skater is at x equals 0, this is an equilibrium point, and it happens to be stable. All right, so here's an unstable equilibrium. So here is our equilibrium point at this point. Here's a picture that coincides to this. It looks like somebody on top of an arch. What makes this unstable means that you're not going to make it back to the equilibrium position. So if you displace them in one way or the other, the net force is going to push them farther away from where they went. This looks unstable, right? If you were on a ramp like this, that wouldn't be very stable for you to be at the top. And so if you think about this being at the top, if you had a small displacement to the left, we would have a slope which is positive, but it's negative of the slope, so the force would be negative. So that would mean that the force is in the opposite direction of the displacement, as opposed to the other way around. I think I might hear the recycling. Hold on a second. I think I was just hearing things, but I wanted to check. They came once for recycling so far. So that would make this unstable. So a neutral equilibrium is going to mean when you have a small displacement and there's going to be no force. So if we look at the skater here, if I displace him a little bit one way or another, my slope is still 0. The negative of the slope is my force, and my force is 0, then I'm in equilibrium. So here are what some of the pictures look like with our potential energy versus position x. So we have a plot of this, and this coincides with that. So how would you make one into the other? So we have force times distance. So our force is going to be the negative slope. So let me switch up colors. The slope at this point would be 0, so that means my force is going to be 0 up to x1. Well, not quite x1, huh? Yeah, less than x1. It's a little bit less than x1. Then I'm going to have a slope that is negative. That's going to represent a force that's positive. So my force is the negative of the slope. And then I have that building up to x2, it's going to be positive. At x2, this is going to be a slope of 0. Fix this up a little bit. All right, so we start at 0, and it's going to go build up here, and then come back down to 0. So we're saying this is 0, this is going to go up, and then it goes back down to 0. Now I'm going to have a positive slope, so that's going to be a negative force. So now I'm dipping below. It looks like, again, at x4, f is equal to 0. So x3, x4, I'm back down to 0. At x3, I'm 0. So this is going to dip down like that. Then between 3 and 4, this would be a negative slope. So it's a positive force. So this is going to go back up like that. And then it looks like from x5 on, my slope is 0. So my force is going to be 0. From x4 to x5, this is a positive slope. So that's going to be a negative force. So this is going to dip down again. And so the graph that I drew looks similar to this one. All right, so very often they'll give you these potential energy curves, and the energy of a system is almost always, it's going to be less than what the value of the curve is, which is the kind of weird part. So like this one goes up to 6, but your mechanical energy is only at 5. And so this particle is not going to exist at all on that part of the curve, which I think is a weird thing, right? Why not just have it be what it is? The total energy stays the same. So that means that at all points for this graph, our potential and our kinetic have to add up to 5 joules. So if I'm at this point here, it looks like I have potential energy of 1 joule. I have to get up to 5 because that's the total energy. So that means my kinetic energy is 4 joules at that point. If I'm at this point here, and it looks like my potential energy is 4 joules, that means my kinetic energy must be 1 joule because I have to stay at that total energy. So if your potential energy is decreasing, your kinetic energy is increasing. If your potential energy is increasing, your kinetic energy is decreasing. And if your potential energy is unchanged, your kinetic energy is unchanged. And so here we look at, this would be a turning point because we have kinetic energy of 0. It's not going to be able to go any further to the left. We have a maximum, we had minimum potential energy. And then if we lower down the total energy to 4, our particle would be trapped in between these two things, because once it gets to the end, it's going to have 0 kinetic energy and it's going to switch directions back to the other. All right.